Alright, boys, so I did a 3D model of the Archimedes pulley system, and here again is how that system looks and operates in practice, just from the video I got the idea from.
There's a type of pulley system we haven't talked about yet. It's a compound pulley system. You remember the block and tackle? We had an 8-to-1 mechanical advantage. Well, this has the same mechanical advantage, but it does it a different way. You remember we add up the tension on these ropes and we have
Oh,
1 plus 1 is equal to 2, but if we have 2 plus 2 is equal to 4 and 4 plus 4 is equal to 8, we can come up with an 8-to-1 mechanical advantage just like that with less pulleys. This is fascinating.
okay. And so here, I was able to recreate that. Um, we got 1, 2, 3, 4, 5, 6 pulleys as promised. And the first pulley makes it 2 times, and then 4, and then 8, then 16, then 32, then 64. So it's a 64-to-1 mechanical advantage. Down gearing by way of pulleys through the Archimedes compact pulley system. And the string will enter in through the top hose here, and it will come down. Now, I did something special where this is a pass-through pulley. It's kind of like the block and tackle one, because I wanted to cut in half the total draw of that first one. So basically, these two act like block and tackle. So I'll show you guys what I mean. Whoa, wait a minute. Okay, because like before, the very first one was going to come like actually this long to get the total draw of string we want in total. It was going to be like this long. But I needed to reduce the total length of the pulley. This is a ruler that's 15 centimeters long. So this is approximately like 11 centimeters or 10 centimeters. No, I think it's 12 centimeters. We wanted 12 centimeters to be our max length, and then we wanted it to be a max width of approximately 1 centimeter, and then we wanted it as flat as possible this way, maybe like 5 millimeters or 6 millimeters tops. Um, so I had to reduce the total turn size of the pulleys and make them a lot smaller. So this is 0.63 millimeters OD, 130-pound test fishing line, and then this tubing is 1 millimeter ID, 2 millimeter OD, and half millimeter walls. So half plus half is 1 millimeter, and then 2 millimeters. Oh wait, that's 1 millimeter. That's a half. That's a half. That's 2 millimeters OD. Yeah, and then 1 millimeter ID. 0.63 millimeters is the OD of the thread. So this is all to scale, and so this is the size of the pulley inner support disc that I had to reduce it to. Before, like the one I actually made in my prototypes is like this big. It's way bigger. So we're taking much tighter turn, which I had to do, even though it's a little bit theoretically harder on the rope to make the tighter turn. I think it's okay because polyethylene fishing line is considered very supple. So that means it can take tight turns with ease. So I think we'll be okay. So this is Teflon tubing, this is Teflon tubing. So it's going to come through the Teflon tubing, it's going to turn 90 degrees around the support, and these supports will be connected to the Teflon by way of tape and then glue on the fabric tape to make it into like a composite cast. That's how I've been doing it with the 401 glue. Okay, and then this goes vertical all the way. The tape is a compression shirt for workouts with adhesive transfer tape stuck onto it to make it into a fabric tape. Okay, so it's going to turn 90 degrees, it's going to come down, and then it's going to come through this U and back up. You can see how that looks. And I could show you through here, and then it comes through this U, and then after it goes through this U, it comes back up and through this U now. So it goes around that hoop and then down through here. And this is that top hoop, which is actually locked into this. This one does not move. All the rest move as far as the pulleys. But the string can slide through that, and it's still moving. Hasn't been tied off yet. Comes through here. Now it goes around the second hoop. So these two hoops are part of a continuous wrap. It comes through this one and all the way up, and then it ties off. So basically, to summarize, the string comes down, wraps, 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 then ties off. So this way, it gets a total of, I guess, the height from here to here looks approximately 7 centimeters. So it'd be 7 centimeters, 7 centimeters, and then 6 centimeters, 6 centimeters is the total travel then of the string using the motor as a winch. So that's 14 plus 6 plus 6, 24, 26 centimeters. And 26 centimeters is about 10 inches, and that's what we want. About 10 inches of total draw coming from the motor. And that will bring these two pulleys all the way up to the top, which will force these four to also be dragged up. So as this bottom one, and these two will be linked somehow, tied together. Right now I have it tied, just this one, tying off right here. I'll have it tied off. I didn't actually model out the tie, and then it'll tie off right here. And then this one goes through that and it'll tie off right here. I just stubbed it out for simplicity because it's like a front view model. I didn't add all the tying, like the knots I'd be tying, but knots will have to be tied. So then these two will both travel up together as the initial phase, and that will already reduce the speed and increase the mechanical advantage by 2, 4. So it'll be 4 times the mechanical advantage and 1/4 the original speed of the motor. Okay. Then these guys will pull up as well, and each one of these, so this will come through here, around here, and tie off right here. So this is basically just tied off through this center point. So this is tied here, and then it goes around through here, and then comes up through this, and it goes all the way up to the top and ties off at the top. So as these two pulleys, which were that first phase we talked about, as they lift to the top, this one will lift about halfway as much as they do. So they're going to go all the way to the top till they hit, but this thing will only lift about this far. And then this one swings around the other way. So this one ties off on here. It goes through this. I had to rotate it a little bit in order to get its back string not to cross over too much. It does nip the edge of this, but it can't really go through anything. It needs to go around it. Okay. And it does nip the edge of this a little bit. So it ties off on here. It'll have a knot right here. And then the string will go down, around, up, and through all the way to the top and tie off at the top. And then the same thing. This will come through here. It'll tie off right there. And the string will come down through, and it'll go all the way up to the top. Tie off up at the top. And then this one ties off right here. And the string goes down through and up and ties off at the top. and it just keeps repeating that. And you could add more. So, like, if you added another pulley right here, that would be 128. Wait, let's do the math again. 2, 4, 8, 16, 32, 64. This one would be 128. So 128 to 1 mechanical advantage. And the next one would be 256 mechanical advantage if you put one here and one here. And that would bring you up to a total of 8 pulleys. We only use 6. And for reference, a standard hobby down gearing from its gear train in a hobby integrated servo motor has a 180 to 1 down gear for its mechanical advantage. So we're going to end up with a 64 to 1. And a hobby servo gear train is 180 to 1. So it's 3 times more than what I have. But I could easily add one more pulley and I'd get 64 would double to 128 to 1, which would get a lot closer to the 180. But I don't feel the need to approach that 180 because I think that, well, this is interesting. So if I feel, okay, so check this out. This is important. If I feel this is giving me more than enough strength, then it's fine. We stick with it. And we'll benefit from the extra speed since we didn't trade as much speed down. We'll have still massive speed and plenty of strength. If during testing we find out we need more strength and this is insufficient strength and we have way too much speed at full speed and it's just ridiculous speed, but we're lacking in strength, we can add a pulley or two to trade down speed for strength and we can continue to add pulleys until it gets to the point that we're pretty much capped on how much strength we can get out of our motors, but it's getting to the point that the speed is now becoming too slow, and then you'd have to remove some pulleys until you get your speed back to a decent level. Now, because we're dealing with finger pulleys primarily on the design right now, and what we're focused on is the fingers of the hand, I'm currently leaning toward let's not trade all of our speed away too hastily in exchange for strength, because fingers don't need to be all that strong. They do need to be strong, but we also want speed. So we want a good mixture of strength and very high speed for the fingers. Because if you have really fast fingers, there are certain cool things you can do that, and the robot's fingers could theoretically be significantly faster than humans. So it would be able to like draw really fast, or type really fast, or tie a shoe just insanely fast, or thread a needle insanely fast. Like it would be able to do superhuman stuff that would be so fast your eye could almost not see it. And I'm not planning to do anything illegal like this, but it's just for the sake of like explaining just the cool factor. Have you guys like read about like in a book pickpockets, like Charles Dickens books, where the little boy was like a pickpocket and he would steal wallets, and I guess you bump into people and your hand just moves so fast people don't see it, and it reaches around and grabs their pocket. Some guys even did that as comedians, like with the magic show type performance. People were laughing. They would like somehow like steal, like not steal, but they would take wallets and a bunch of stuff from people's purses and stuff and put it in their pocket, and nobody could see because their hands move so fast and their fingers operate so fast through practice. And then they would go up on stage and say, now whose is this? And people would be laughing and the person would come up to get their stuff. So I've seen performances like that. So having the robot capable of something like that is cool. I'm trying to reach max human capability, if possible, and maybe even exceeding human capabilities with my hardware designs. And so that's kind of like a benchmark. is all I'm saying. I'm not ever planning to have the robot like steal, but maybe it could like pickpocket as a joke. But I don't know if a robot ever could do that as good as human, mainly because like it's such a feel type thing, and I don't think robots would be able to feel. Their touch sensitivity, I think, would be inferior to a human, but that may not be true. And I'm not very up to date on cutting edge touch sensory stuff. I know that strain gauges are what I'm planning to use for the fingertips, and I don't know how sensitive they are or how accurate they are. I've not worked with them yet, um, but they can sense pressure or force placed on the fingertips. So, anyways, one other benefit I have is that from a past video, I showed you guys why I don't want to use integrated servo motors, the kind that comes in a box with all the gearing and all the circuitry and the motor itself and the potentiometer all in one box with the servo horn that comes with it. I didn't want to use that because the motor that comes in those boxes is very tiny brushed DC motor, which is much lower quality than a brushless motor. And you can buy a brushless motor that's way bigger than that motor that comes with that box. And the motor that comes with that box only pulls like 15 watts. The brushless motor, that's way bigger than that motor, pulls 200 watts. The 2430 motors I selected. And it should be like 10 or 20 times more powerful than the motor that comes stock with a standard hobby level servo motor, integrated servo, like the MG996R, which is kind of like a very standard one used for a lot of robotic hands projects that you'll see all over YouTube videos. So it's like 3 times the size of the MG996R brushed DC motors that are in the MG996R common hobby servo motor that people use for robot fingers. So the fact that it's 3 times the size and probably 10 times as strong, pulls more than 10 times the amount of watts. It's a beast. I don't think we need to down gear it anywhere near as much as they have to down gear that small brushed DC motor in order to match the power that that thing has. So I think that just down gearing at 64 to 1 compared to their 180 to 1 will still be 2 or 3 times stronger than their servo, while still retaining now maybe 10 times the speed that they can have. So we'll have 10 times the speed and 3 times the strength. So we got room to play around, basically, because we have such a beefy, monstrous motor to work with. That gives us the luxury of not down gearing as much while still getting more than enough strength out of it. But like I said, if we need to down gear more, we can always do that later. We can always add one more gear. Now the problem with adding too many of these pulleys to down gear it and gain more mechanical advantage is you start extending the length of this so much that you're going to have trouble with fitment issues. And that's what I discovered. I was having big fitment issues with the much bigger pulleys I had designed before, which were like this big. It was like 5 times the size of this. So I had to downscale everything. This is my downscale model, and I think this one will work because I've actually done a test on this scale. Actually, like you see the shape of this with the turquoise, you could see I actually created a shape here, a little rectangle, and you'll see I put a bunch of these rectangles into the robot's forearm. Each rectangle represents one Archimedes system, like the one we were just looking at. It would fit inside this box, and I was able to fit this many. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And this is the robot's forearm. Okay. 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. Divided by 2 is 18. Yes, so that's enough for 18 motors because each direction of turn for the motor will require an Archimedes pulley system for that direction. So each motor requires 2 of these Archimedes pulley systems that we showed here. Each direction motor needs one of these. So since the motor has forward and reverse, it needs 2 of these systems. So then each system has 6 pulleys down here. And so each motor then will have 12 total pulleys, 2 total Archimedes systems. This is the Archimedes system. And so we, just in the forearms alone, managed to scrape together room for 18 motors worth of pulleys. And that's a huge accomplishment. We managed to fit them in here. And it all fits a little bit. You'll see some edges like this is sticking out, unfortunately. So that one might actually have to be deleted. Or, the elbow will just be a little bit bigger there, which might not be a problem. Like, we can, on the final model, you're potentially going to have to do this a little bit to allow room for it. Does that completely ruin the look? I think it's still okay. That didn't, make it look like totally weird. Looks like this one's sticking out a good amount too. But, this is like 0.5 millimeter anyways. So I'm not sure that that's a big deal. If it's sticking out a lot, it's one thing, but this is just barely. Because this whole thing is only 5 millimeters width. So this is like maybe 1 millimeter sticking out. So I think that's okay. It's just ballpark because the base mesh is very blocky anyway, so it's not exact. It's kind of rough. So I'm okay with this. Sticking out a little bit. I fit as many as I could. So the idea was when I had the length of these much longer, then I couldn't run 2 rows. So I wanted to run one group from here to the midpoint, and then one from the midpoint to the wrist without getting in the way of the wrist. And I succeeded at that. So as you can see, we've got a little bit of room to add 1 more pulley down here, maybe even 2. So we could add more pulleys in the future if we need to, but I think 6 pulleys should be good. It's already 64-1 mechanical advantage, and I think that'll be enough because, like I said, these are compared to okay, think about this, guys. These motors are 2430 brushless DC motors. They pull 200 watts each. One motor is going to be for this joint and this joint, and then one motor will be for this one. I combined these to be handled by one motor because at first I was going to have this be a motor and this be a motor, but I realized the last 2 joints of a finger pretty much always move at the same time, so having one motor handle it I think will be sufficient, especially if you're using really beefy motors. You won't lose that much in wave strength. And these motors are so much bigger than the motors I was going to be using now that I upgraded to brushless instead of that small N20 brushed DC motor. I upgraded to brushless exclusively for the fingers. So these got significantly bigger in size, 3 times the size of the brushed DC motor I was going to go with. And so because these are bigger in size, I couldn't fit as many in the forearm, and I didn't want to put too much more up in this part because this is already getting full. And the last thing I wanted is to start bumping more motors into this region and then having more motors in the torso, because we want to save room in the torso for emergencies like other things I'm not remembering or more batteries or whatever. I don't want to plan for every square inch to be filled, because then what if we need room for some unexpected thing? So we want to try to keep motors for the hands as close to the hands as possible, and not have them trickling up the arm and into the torso and whatnot. Because then there's a domino effect where you move motors for the hands into the bicep area, then these motors have to go into the torso area, then something in the torso area has to move down, and now you're filling up the center of the torso. Now you can't fit as many batteries. There's just like a ripple effect that happens when you start using up room too deep into the robot that was supposed to be more localized to here. So I wanted to keep the pulleys for the robot's hand closer to the robot's hand. Plus that reduces friction by having the pulleys not located so far away. Even though we could do it, even here, we could have the pulley we could have this motor for the robot's finger, like this motor right here. We could put the pulley for that motor in the ankle if we wanted to, and it would work, but how much friction would be in the travel all the way down here? The pulley system is here, and then the travel all the way back. There'd be a lot more friction, and you would lose a lot of your strength that way, and probably generate a little bit of heat and wear and tear on the tendon, the fishing line. So anyhow, back to what I was saying. This is 200 watts it pulls instead of the 20 watts that the little integrated MG996R servo motors would use. That's a lot of wattage. So these are some beefy motors, relatively speaking, to those little brush DC motors. And with that amount of watts, I almost believe that just using this as a winch without even any pulleys, I think it might produce enough torque at the winch to actuate a finger joint sufficiently to move the finger, but maybe it would have no toughness to it. It would be too weak for practical, like lifting up heavy objects and stuff. And doubling it or tripling it through the pulley system already might give it enough strength to start getting closer to matching, like a baby's fingers. But we're doing 64 to 1. 64 times that strength. So there's no telling. It's going to be significant. It's going to be a lot stronger than the MG996R motors. I guarantee that. And that's 180 to 1. This is only 64 to 1. But because we're not going down 180 to 1 with these, we're not trading as much of their speed, so we'll still have huge speed. Our fingers will be able to move insanely fast. Literally, I think that since we only did 64 to 1 on these motors, the speed of the fingers will be like a blur. I think that they'll be able to move, like make a fist, and then bring the hand back out so fast, the camera may not even capture it. It can move so quickly. It's going to be like the Matrix, like the guy dodging bullets. That kind of superhuman speed, where you saw like 3 Agent Smiths because they're like moving around so fast, you see 3 of them. Or like, how if you watch a ceiling fan move, the blades start to look like one like shape, like you don't see the individual blades anymore. Or like with helicopters, you'll see like one blade that seems to be moving really slow, and that's how it's captured like on a video camera. It looks like it's just moving really slow, but that's because you're like just seeing wherever the frames happen to be capturing where the blade was. But the FPS of the camera recording it might have only been like 30 FPS or whatever, and the FPS required to capture like how fast it's really moving would have been like 1,000 FPS or 10,000 FPS. So anyways, we're going to get some weird effects like that with the amount of speed that these fingers will be able to move because we're not down gearing this so much. And like I said, we don't have to down gear it so much because they're already pretty strong to begin with. So the stronger the motor is to begin with, the less you have to down gear, and the more you can just save the speed that it wants to have naturally. So it's got a lot of speed to give. We're trading some of that speed for torque through the pulley system, and the speed that we didn't trade away we get to use to make our fingers lightning fast. That's where I'm at with this. That's the logic. Maybe for like a bicep where we're not as concerned with high speed biceps, maybe we would extend the pulleys out 2 or 3 more in order to really maximize the strength of the bicep, since that might not be something we want or we're concerned about having good speed retained. But the fingers might as well, retain some of that speed. Now, as you can see, compared to the motors and then the Archimedes pulley system, these pulleys, the system is relatively small. It's like the size of a pen, it looks like. About the size of a pen or a pencil. Not even as long as a pencil. So it's kind of a small system when you look at it this way like with the rest of the 2-scale humanoid robot body. This is the size of an actual 5'5" human. So these are pretty small, comparatively speaking. So it's a nice compact design. And the non-compact version I had planned before I wouldn't be able to fit this many in this tiny area. So I really had to make a tinier design. It was not optional. So I'm gonna have to redo the pulleys. I've already 3D printed. I've already 3D printed over like 100 pulleys. I'm gonna have to throw those all out and print way smaller ones. As far as the little disc that supports the inside of that turn radius. What else can I say? So yeah, that's why blocking out where you're going to put stuff in your model like this is so useful, because you can see if something's going to be too big and redesign it before you like spend too much time in the fabrication phase. I was able to learn in the design phase that I needed to make a change immediately. And it was an emergency, because the last thing I wanted is to put like 1/4 or 1/8 this number of pulleys in the forearm and have to move a ton of pulleys into here that are still handling just the hand motors. And then that means there won't be enough room for the pulleys required for these motors in this part of the arm, which would mean they'd have to go to here, and then they'd be competing with the pulleys needed for these for space, and we'd just be using up all the space in the chest of the robot that we're not wanting to use up. Whatever space we still have in the torso, we want to avoid using it until the very end. And if we have space to spare at the very end of the design, at the very end of the project, then that means we miniaturized and compacted things down very well. And I'd rather finish the project with space to spare, which we could always slam some extra batteries into or whatever, than to finish the project completely out of space and completely out of options and feeling very stressed out. Like, I hope I don't come up with some idea that requires some component that we simply do not have the room for. I'd rather have room to spare, just in case some idea pops up where we would need a little bit of room. I want to keep some room. So the room is very precious. You want to guard it as much as possible. So I'm trying to cram as much into here as I can so that I'm not starting to rob room from other areas. In fact, along the same vein, I want to try to put like circuitry inside the palm that will manage like the strain gauges and stuff. You need a OP amp for that. And so I want to have like the circuitry that does the OP amp stuff all in here. With the Wheatstone Bridge is what it's called, something like that, for the OPM. So yeah, that's my update on my Archimedes pulley. I wanted to do an animation of this so you guys could see like more it in action, but that video I showed you guys is good enough. You got to see this in action. You don't need to see these animated. You get the idea. And you'll see it in action when I'm actually like doing test runs anyway, so I'm just not going to be putting that in, because I can visualize these moving. If you guys can't do that, you need to practice your visualization skills. Alright, so that's it. A little update.